Okay, I think almost everybody's here now. So just out of curiosity, how many of you are planning to use Hydrolite some way in your projects, to run your IOPs through it and compare Hydrolite output with RS? Okay, so this is basically the lecture then, is to tell you guys, don't panic when you do that. And Thursday night, you're still off by a factor of 2. So that's fine. Don't expect you're going to get agreement to within 5%. So it's a tough problem to get all this stuff to agree. So this lecture is on closure. A few words at the end just to think about. If you're designing an experiment somewhere down the road and NASA has given you $10 million and you have 20 people working for you, how are you going to put together this big field experiment? Okay, so closure is, as we've said several times, it's just a fancy word for getting everything to agree. And there's several different kinds of closure that people will talk about. So one of them is scale closure or spatial scale closure. So think if you go out here offshore and you use a satellite, you retrieve the chlorophyll, and then you go out on the boat and you measure chlorophyll at some one point. Well, that satellite chlorophyll might be for a square kilometer, which is the nominal MODIS pixel size. So MODIS has looked at this square kilometer and gotten basically radiance coming from all the different points in that kilometer, and then some way come up with chlorophyll value. So you kind of have to ask yourself, well, if I measure chlorophyll at just one point, can I really expect that to agree with the MODIS chlorophyll, even if the atmospheric correction's perfect and so on, and your algorithm's perfect and all of that? Because if the water's horizontally homogeneous, you would expect them to agree. If the water's patchy, and you can see there's a lot of difference if you just go a kilometer out here and what you can get for IOPs and chlorophylls, well, then you have to ask yourself, if I really want to validate that MODIS pixels value of chlorophyll, how many spots in that square kilometer should I measure the chlorophyll so that I could average all those together and get something that sort of corresponds to the MODIS chlorophyll? Another kind of closure is instrument closure. So you've had different instruments now for measuring things like backscatter. There's a BB9, there's an older instrument called the Hydroscat 6, which claims to give backscatter at 6 wavelengths. There's the Hyper BB. And so you stick all those instruments in the water at the same time. Are they going to give you exactly the same backscatter coefficients? Well, probably not. And if not, then why? Well, you have to understand the different instruments and what little fudge factors they use to convert a volume scattering function, maybe at one scattering angle, into a backscattering coefficient and so on. So that's a very difficult process, as you guys are learning, to get different instruments that in theory put out the same numbers to actually do that. Then there's model closure. Do different models give the same answers? So there's Hydrolite, there's all kinds of Monte Carlo models out there. I have Monte Carlo code, Howard Gordon has it, George Cadwar has it, lots of other people. And there was actually a big modeling comparison back in the early 1990s where about 6 or 8 of us got together and we cooked up a set of problems, and then each one of us ran our models on those problems to predict in-water irradiances and radiances and so forth. And they finally actually all give exactly the same answer, but you would be surprised at how long it took some of the people to find some bugs in their code. And so after that paper was published in '94, everybody then said, we can trust these models. So when you write a paper and you say, I ran Hydrolite, or if Howard Gordon runs a paper and says, I ran my Monte Carlo code, nobody ever says, how do you know that code's giving the right answer? Because either they're all giving the right answer or they're all giving the same wrong answer. So that's model closure. That's really the easiest of all the closures here. And then there's the model data closure. So you have some data for IOPs, remote sensing reflectances, et cetera. you run those into Hydrolite and you compare its RRS with what you measure. So you're using data and a model and trying to get those things to agree with each other. And those of you who are doing that this week, you'll see that these are probably not going to agree. If they do agree, it was just beginner's luck. And I have people all the time, they'll send me a thing and say, well, I did all of this and Hydrolite's remote sensing reflectance is off by 30% from what I measured. So what's wrong with Hydrolite? Well, my response is always 30%, stop now and publish your data, because that's as good as you're ever going to get. If it's a factor of 10, yeah, there's something wrong. Yeah. Oh, well, that's your choice as a scientist. Are you happy with 30%? Are you happy with 10%? Are you happy with factor 2? A factor 2, that's not so good. If you're in that like 30% area, I'm happy with that. If you're in 10%, you've really done some serious work. So, Colin.
And if you have uncertainty, right, on your measurements, then that helps you a lot.
So it depends on the product you're trying to get. And if you want to use the depth from a line level, and you're the late and you need it within 10 centimeters, then either you can't or you can't. If you're not very too bad, or if it's good enough, that's the number of people that are happy to do it. So the application matters and dynamic range. I mean, this is why I keep fighting with people on kilometer on art, telling them it is useful. They come back and say, but it's, there's certainly so large. Yes, it is, but given how wide it varies, it can still be good size. So we have to be honest about the uncertainties, and we have to take into consideration, even as Chris says, what it is we want to do. And how far it moves forward. But there's another thing here that is really important. It is what you compare. So you can compare these beers with Olchi, with Moody's in the water here. But they're all of them pretty much use the same methodology to measure. Just like these three DB sets, they all do one angle and then they refer to that stuff. So they're independent. It's some sort of closure, but it's not as independent as if you got to the same number with really a different way of measuring. Because, for example, all the satellites use Mobi as their calibration part. So they could all find it, but you would not know because they're all different. So always think about how independent is independent. What are they assuming the same? So you can do all these model closure, Hydrolite versus the other, but there's something fundamental that might not be there in the environment that they all assume. They might all be similarly relative to the environment, not relative to each other, but relative to the environment. So it's really, really important to all that think. What are the differences?
Okay, so what I'm going to do today is just walk you through several examples of some simulations people have done using Hydrolite where they really did everything that's necessary. And then finally at the end, they end up with good agreement, but you'll see what a process it is. So here's, if you really want to do a model data closure study, got to back up and think about what did I need to measure in the field to use in the Hydrolite or go into Hydrolite. Well, I need to know the absorption coefficient as a function of depth and wavelength. So you get that from an ACS or spectrophotometer. You need to know the scattering coefficient. You need to know the scattering phase function. Well, that's almost never measured, but maybe you can get it from BB over B, where each of those is a function of depth and wavelength. And then you can tell Hydrolite, pick a Fourier-Farad phase function with this backscatter fraction that can vary with depth and wavelength. You need to know the boundary conditions like the sea state, so what waves are on the surface. Well, you can parameterize that pretty well with the wind speed. You need to know the sun location and sky conditions. Those things there are not going to matter if you're looking at remote sensing reflectance, or they matter a little bit, but not much, because that's an AOP, and the whole purpose of the AOP is to kind of get rid of those environmental effects. On the other hand, if you want to compare with measurements of ED as a function of depth and wavelength, then you have to have the sun in exactly the right spot. You have to have just the right sky conditions, because that's determining the magnitude of ED. Okay, and if you're in shallow water, you have to have the bottom reflectance. And then you think about, well, okay, what are the hydrolyte outputs? Well, you know those now. They're radiometric variables, radiances and irradiances. What do you usually measure? Something like LU and ED. Rarely do you measure a full radiance distribution, just if you're Ken Voss and have the one instrument that can do that. You have AOPs like KD and R and RRS, and the most commonly made measurement that you guys have been doing is remote sensing reflectance. So you may have gotten that from something like a TSRB that measures LU in just below the surface and ED in the air. And then, of course, you have to monkey around some way with extrapolating LU up through the surface, or you do the gray card thing above the surface. Then you have to come up with this magic number rho that tells you how much you racked out. Well, you know, that's black magic there. So just keep all those things in mind. So here's an example now of a paper. There was a ONR funded field program called HICODE, which stood for Hyperspectral Coastal Ocean Dynamics Experiment, at a place off the coast of New Jersey. Everybody went out there with all their toys and got all of these measurements and then dump them on my lap and say, make sense out of it. So, okay, what was measured? They had total absorption in beam C from an unfiltered AC9. They had from filtered, they had backscatter from a Hydroscat 6, an Eco VSF. And then there was an instrument called the volume scattering meter, was developed by some Ukrainians, and you pay them $5,000, they'll show up with their instrument and give you a volume scattering function. So very unusual to have that. It's only at one wavelength, but take what you can get. Then there's EDs, LUs, sky irradiances, various sensors there, and at these wavelengths. And then there was a sky ED and LU from a hyper TSRB. So that's what I had to play with. IOPs to come in, irradiances and radiances and such to come out that I could then compare with what was measured. So here's what the profiles of the IOPs look like at this LEO 15 station, which stands for Long-Term Ecological Observatory in 15 meters of water. And there's a number of these LEOs, long-term ecological observatories around the world that have been there for a long time, and people keep monitoring them to look at long-term effects like climate change. And they're not just in the ocean. There's like a grasslands LEO in Saskatchewan or somewhere. There's one in Antarctica. There's one here. They're sprinkled around. So anyway, here's the profile of particulate plus CDOM absorption. And you can see up in the upper 5 or 6 meters, it's kind of homogeneous, and then things drop off. There's the CDOM profile. There's the particulate. Here's the scattering coefficient, which is of course by particulates. And then here's the chlorophyll, and here's beam C. Notice how things like this and this have exactly the good correlation with the chlorophyll. So you can see up near the surface, there's a mixed layer about 7 meters deep, and it has a chlorophyll of about 6 to 7, and then that drops off to about 2 down below. So very nicely correlated with particulate absorption and scattering. Not quite as obvious with CDOM, but still it's there. And then you look at the backscatter coefficient. Well, here it comes, and then there's this big bump at about 14 meters. So why the big bump here, the increase in the backscatter coefficient in this last few meters in the bottom here was actually about 18 meters. Any speculation on what that is? Ben? Yeah, it's resuspended sediments right near the bottom. those currents and they stir up sediments and they mix up in the bottom 2 or 3 or 4 meters of water. So that's what's going on there. Notice up here, there's no correlation at all with what the chlorophyll profile looks like. Why? Well, backscatter just doesn't correlate well with chlorophyll because backscatter depends very strongly on particle shape and all these other things that and size, which have nothing to do with how much chlorophyll's in it. So kind of contemplate this, eventually convince myself that the AC9 data is pretty good. Here's this volume scattering function meter data. So the blue is measured from this VSM instrument. The red is the best fit of the Fournier-Ferrand phase function for this particular set of IOPs. And then the green is the Petzold phase function. And you look at that and say, well, that's really pretty good, but really down here you look, that's a factor of 2 or more off. So the Fournier-Ferrand in red and the measured in blue agree pretty well, except in that last 20 degrees or so when there's this rise in the measurement and there's a funky little dip there. That's probably some kind of internal reflection in the instrument or something, but who knows? The Fournier-Ferrand always kind of levels out here. That's a little bit of a weakness it has. But anyway, that's what I have to play with. Okay, so then I looked at, this is depth. Here's the chlorophyll profile. What's the wavelength dependence look like on things? There's from 442 in blue to 683 in green. And that's the backscatter fraction, which you see is down around 0.5% here out to 1.3% or something there. And then I looked at how does that depend on depth? This is the depth profile at the different wavelengths. Here's the wavelength plot grouped by depth. And you see down near the bottom, Z is greater than 14 meters. Those are the ones where we're up around 1.345%. Up near the surface, it's about 0.5%. Why is that? Well, up near the surface, that's where the chlorophyll is. Low index of reflection particles don't backscatter very much. Whereas down at the bottom, the high index of refraction mineral particles backscatter a lot. So you're getting a bigger backscatter fraction for those mineral particles. Okay, makes sense. And then, there's a gradation in between. Okay, so now time to compare with some hydrolyte output. The black curves here are what was measured. The green curve is what hydrolyte gave with the Petzold phase function, which is typically often used when people don't have any information on what the real volume scattering function is. The red is hydrolyte with the Fournier-Ferrand phase function determined by the backscatter fraction. And then the blue is the hydrolyte run using that measured phase function from this VSM instrument. So you look at this and you say, well, most of these wavelengths, the green, the red, and the blue are all pretty darn close. And then Petzold is totally off here. Well, what's going on there? Well, the Petzold phase function, if we back up, it has much higher values here in the backscatter direction. And the backscatter coefficient, or the backscatter fraction for Petzold is about 1.8%. In my data, nothing had that much backscatter. So here the dashed line is the backscatter fraction for Petzold, and I'm less than that and sometimes much less than that, down to 0.5%, never up to 1.8%. So Petzold has too much backscatter. Then you look at the profiles of ED here, ED, and they're getting, let's see, ED, yeah. So those profiles are less as you go down. Everything's kind of okay at the surface, but you go deeper. So why is ED less as you go down than the real measurements? Any speculations? Okay, here's the deal. Petzold has too much backscatter. So the light's going down and it's backscattering upward. What's backscattered upward is lost from the downwelling part that makes ED. So that means there's not enough light going down and therefore ED is too small. Now, if that hypothesis is correct, what would I expect to see for LU? It'll be too big. And lo and behold, up near the surface, LU is too big when you use Petzold because it's getting that extra backscatter that the real world didn't have. Okay, that all makes sense. Now, in all of these curves, the instrument measurements may start out okay, and then it goes way bad. That's roll off because there's simply not enough light down there for the instrument to measure. Back here, you didn't see that very much because there's generally a lot of light heading downward and you're collecting all of it to measure ED. Whereas to measure LU, you're just getting the light that's coming up in a very small set of directions. So that's a harder measurement to make. And you see that at the wavelengths where the light has been absorbed, particular by CDOM down here. At the clearer wavelengths, that doesn't happen much. And then back out in the red wavelengths where water's starting to absorb, then you see the instrument saying, I'm done, you're just looking at dark current. Okay, so that's the way that came out. It all makes sense. Here's now a prediction of LU over ED at 0.5 meter depth. So that's basically the bottom sensor on your hyper TSRB. Versus wavelength. The black is what was measured by the hyper TSRB. The purple dots were measured by an instrument called the Ocean Color Profile made by Satlantic. So they're pretty close to the measured values. The green is what I get with the Petzold phase function. Way too much for this ratio because LU is too big and ED is too small. Now this is ED at the surface was okay, but LU at the surface was way too big. So we get much too big of a value for what's effectively remote sensing reflectance. And then when I used the Fournier-Ferrand guy, then I got the red curve, and that's in pretty good agreement. So this sort of agreement here is about as good as you're ever going to see. The moral of the story in all of these is if you guess the wrong phase function, game's over. We're off by a factor of 2 here at some wavelength just because we guessed the wrong phase function. Okay, here's a comparison of some instruments and TSRB predictions or TSRB measurements and other instruments, and then comparison with hydrolite. This was in California waters. And what you see here is the black, the purple, and the yellow, the black, the purple, and the yellow. Those are measurements, and you can see kind of what sort of spread there was there in those instruments that in theory would give exactly the same spectra. And then with a couple of runs through hydrolite, making a best guess at what the phase function might have been, it's sort of in the middle there as well. So you can see a range of values due to different instruments and a range of values between the cyan and the reddish thing here. That's just differences in what this person guessed for the phase function. So typical spread of values in this kind of study. And you can see if you come down here, it's like 0.04 up to 0.08 or something. That's a factor of 2 difference in those RRSs by somebody who's one of the best people in the field. Okay, here's another set of comparisons. Maria Giorgio was an ex-student or is an ex-student of this class from, I don't know, 12 years ago or something like that. When? That long ago?
In 2001.
Okay, well, anyway, as the little frog says, time sure is fun when you're having flies. So anyway, she went off, her PhD was just basically a closure experiment in Chesapeake Bay. And it was an enormous amount of work. But read this paper, Giorgio et al., 2006. She really shows you how to do things right. All the working through her data and correcting this and correcting that and, massaging this and whatever. But then finally at the end, here's LWs, calibrated units, not even RRS, the real numbers for LW and the, let's see, the little symbols are the model, which is hydrolyte, and there's data in the little circles there. And these are different stations in Chesapeake Bay. And you can see she's getting darn near perfect agreement between the data, the LW she measured and the hydrolyte predictions. But it was a whole PhD to get that. Here's some more of her data where this is measurements of, let's see, LU here and ED here. Once again, very good agreement between hydrolyte and the measurements. And then here's where she looked at LW for different phase functions. So the little diamonds here, open diamonds on the bottom, those are what she actually measured. Then these curves here are when she used a Petzold phase function. Then she assumed that the backscatter fraction was constant, put in some reasonable value determined from her data for near surface waters, and that brought this curve down to here, so it's a little better. Then she had an eco VSF, used that to get the backscatter coefficient, had the total scattering from the AC9 and used that, and that gave this curve here with the little squares, and that was closer still. So moral of the story, make a bad guess on the phase function. Maybe you guessed right, maybe you didn't. But the better you do on modeling the phase function, the closer you come to getting agreement with what you actually measured. Okay. Another fellow, Alberto Tonizo and Mike Twardowski and company, they did a similar experiment where they compared measured hydrolyte, they measured and hydrolyte computed RSs in both case 1 and case 2 waters. They did the scattering corrections for their AC9 3 different ways. They went through this enormous data preparation process. And then the last step is you kind of compare with hydrolyte. So there's kind of a list of what they did. They have 3 different ways of doing the scattering corrections on their AC9 data. One of them is you just set everything, the non-water part to 0 at 715, then you do this correction. Then they did a correction that was an iterative thing where they actually took the volume scattering function at 1 wavelength and sort of cycle through that. So you start out with a volume scattering function, you use that, you figure out how to do the scattering correction, you get a better set of absorption and scattering. Then you go back and say, now I have a better idea what the phase function is, you tweak that, and you iterate through this thing and hope it converges. And you see here, there's their raw uncorrected absorption measurement. Then the red and the green are 2 different ways of doing the AC9 scattering correction. And then these grayish symbols here were the 3rd way of doing the scattering correction. And, these 2 agree, that one's different. So, read the paper and see what they say about that.
Kurt,
Yeah.
I want to comment on that. So based upon now the measurements that you made in the integrated sphere with particular absorption, when you look at those curves, what do you think about the different assumptions of those scattering corrections? The 2 of them have something in common, which is what? They assume 0 and linear infrared, right? And so is that what you see? Have a lot of that clearly has things, but it also has a lot of non-alpha particles in it. So what did you measure when you had non-alpha particles on your could shift it up. There's actually not non-negligible absorption in the near infrared. And so, there's, each of these have assumptions, but you now have some intuition about what you would expect if you have significant non-optical particles in your particular matter. If it's a phytoplankton balloon, you would hope that your scattering direction would get you down the scale in the near infrared. So it's always a good check for yourself to think about what your corrections should look like before you run.
And this, I think NYB, that's New York Bight. I'm guessing that ain't case one water.
No, and you can see from the shape of the spectra that
Yeah.
it's not just phytoplankton. There's a lot of
Yeah.
non-optical particles.
Okay, we're not going through this, but this is their flow chart of how they process all their data and doing all these iterations. And this mascot instrument is their volume scattering meter. So they start out with the beam C they have the mascot data. They go through this whole mess of whatever, and they finally end up with the backscatter fraction by particles, the phase function for hydrolite, and the beam C for hydrolite. And that's what finally goes into hydrolite. So that's what they did. Here's some of their predictions of remote sensing reflectances. Some of them pretty good agreement, some of them a lot of spread. Here's RS again, and this is just different stations. Sometimes very good agreement, but then things were maybe a bit off here in the blue, that's just the way it turned out. Doing things is absolutely as good as can be done, and you still get those kinds of disagreements sometimes. Here's RRSs at various stations, and they got basically pretty good agreement there. Now and then, something's significantly off, but by and large, they got good agreement. And this is, once again, as good as you'll almost ever see. Okay, so they concluded in their big error analysis, where they looked at all the reasons for these disagreements, that they could get RRS to within about 20%. And half of that error, they said, came from the RRS measurement. So you've got all the radiometric calibration and all of that business. And about half of the error came from the IOP measurements. So like the AC9 scattering correction, and from the model assumptions, namely hydrolite ignores polarization. So there's, like often a 10% error in the radiance in some particular direction. They found that using the Fourier-Ferrand phase function determined by the backscatter fraction gave results that were almost as good as using the measured phase function. So 23% error versus 20%. That's probably not a statistically significant difference. So once again, when you're done reading Giorgio's paper, read the Tonizzo paper, and they also show you how to do things correctly. Colin.
And then you're going to take those measured or modeled RSs and try and invert them to get IOPs, right? And so that has to go into the calculus of your uncertainty. If you're looking at 20% measurement error or 10% measurement error, that again, you have to kind of propagate that along as one of the known uncertainties, or known but maybe the quantity is unknown, but at least you know that there is uncertainty that's going to come out when you say, oh, well, now I have phytoplankton absorption of per meter. You need to think about what that really means in terms of what went into the measurement for the simulation.
Another thing to point out, so these papers described so far, to a large degree, they were preoccupied with getting to it and what is that. When you do your paper on science, whatever, something, I still want you to do this, still asking you to do this exercise. Just prove to yourself that the data are consistent. If you understand the uncertainties in the data. The uncertainties are not the noise you see when you average. It's not a standard deviation when you measure your absorption. It has to do with direction, etc. So this is part of the exercise. Often people will do this now and put it in a supplementary. Just to convince you, I know how to make these measurements. And they're consistent. Because this instrument, as you know, you plug them into your data. How do you know the data is good? Reasonable. No one should. You convince you, the viewer and yourself, that you know how to do good measurement.
Okay, so to put it all together, if you have concentrations like chlorophyll and minerals, and you run those through some biogeooptical model, and it puts out good IOPs for absorption coefficients and backscatter coefficients, whatever, you run those through Hydrolite, you'll get good results. If you take concentrations and you run them through a biogeooptical model that's not appropriate for your water body, and it's easy to go to the literature and say, you know, here's my model for absorption coefficient as a function of chlorophyll. Keep in mind that was derived undoubtedly from open ocean case one waters, probably in the Mediterranean, you know, or some, if it was a Morel paper, and it works fine there, and it's not going to work in the Gulf of Maine. So you're going to get bad IOPs, you run those through Hydrolite, you'll get bad results. And then it's human nature to assume that the problem was with the last thing you look at. You assume all of this is correct, and therefore there's something wrong with Hydrolite. That's just the way brains work, when really here's your problem up here. Okay, so I don't think we need to say this again. It's been said a dozen times that, you know, you have to make sure whatever models you're using for whatever it is are appropriate to your water body. Okay, so you get the idea, and the disagreements are where you often learn the most. So it's not a bad deal that you got bad agreement if you can back up and say, oh, well, guess what? Here's what was going on in my water body, and I'm using this biooptical model up here that didn't have the right mineral particle spectrum, or, you know, whatever it happened to be. And then you've actually learned something from the fact that you got bad agreement the first time through. And then, of course, also redundancy is your friend. You know, if you have 3 different instruments or 2 different instruments for measuring something, you can compare those, and if they're greatly in disagreement, there's some kind of problem there. If they're in agreement, well, maybe the problem's somewhere else, and then you go figure that out. Okay, so I was on one of these, yeah.
I have problems that would not bring to instruments in order not to have this problem. That's bad science. One is much redundancy. This is where we learn from. Yes, when you have 2 instruments, they're going to give you 2 different numbers. Then you have a sense of the 250. As opposed to have one, think that you have 2 because the noise. I'm just reiterating what we said that time, because I wanted to really contribute. As Kurt said, redundancy is your friend. It's what you want. You want as many different ways to measure.
And we get pushback. Always test your measurements, test your models. I use the same models that I've been using for 30 years. Why? Because I keep looking for them to fail. Because when they fail, they learn something. So always don't be too tied to your own ideas. Just keep trying to learn something from that.
Do you remember the Tonizzo study? He finally got to where he had RRS with a 20% error. Now, one of the exercises we'll do in the Monte Carlo lab today is to look at how much accuracy you have to have in A and BB and sun angle to get a 10% or 20 or 30% error in RRS. And it'll be scary how accurate you have to measure BB and A to get 10% or 20% in RRS. So you'll get to play with that tonight. Anyway, so once upon a time, I was on another one of these, in this case, it was an NSF review panel to look at, you know, what's needed coming down the road for ocean color satellites. And one of the things that we put in there was a little outline that said, look, you got to go to sea and validate this thing. So what do you need to measure when you go to sea in order to get all the pieces you need to validate the retrievals coming from the satellite? Well, the guiding principle here that I pushed on them was that if you really want to validate the instrument, you have to be able to do a full radiative transfer calculation where you start with the sunlight at the top of the atmosphere, get that through the atmosphere, get it into the water, bounce it around inside the water, get some of that light back out, and then do an atmospheric path radiative transfer equation back to the top of the satellite. That's really what nature's doing, and you need to be able to reproduce that so you can some way study the effects of all the different pieces along the way. Well, no such data sets ever been collected and probably never will be. And the reason is it would cost you $1 million and you'd need like 30 people and $10 million worth of instruments to actually make these measurements. But at least think about, I need to know this. I can't measure it, but what can I use as a proxy? Okay, so you're going to need to validate the atmospheric correction algorithm. So you need to know the absorbing and scattering properties of the atmosphere, meaning all those different things that are there, Rayleigh, aerosols, NO2, et cetera. You need to be able to validate the biooptical inversion algorithm that retrieves something like chlorophyll once you're given the remote sensing reflectance spectrum. So you need to know both the value of the chlorophyll, you need to know the water leaving radiance that's going to determine your spectrum, and you can then validate that. You need to know how what's going on in the water influences the radiance. So you need to know water absorbing and scattering properties, that is the IOPs. And then you can, if you measure the in-water radiance distribution, well, then you could see if you're, you could run hydrolyte for the water part, see what kind of agreement you get there. It's going to give you a water leaving radiance, which are then going to propagate back up through the atmosphere. Well, as I said, nobody ever collects that kind of data. And part of it is it's too expensive. Part of it is you're on the cruise and you say, well, I'm a plankton biologist. I don't care about how plankton scatter light. Some other guy says, well, I'm an in-water, underwater visibility guy. And all I need to know is the volume scattering function for the first 5 or 10 degrees. I don't need to measure the whole thing. And so you get all these specific science problems, each of which requires 1 or 2 or 3 measurements, but none of them gets the big picture. So you often end up with a bunch of bits and pieces that are not really tied together. Okay, so ideally, you would measure absorption, well, and you'd measure the volume scattering function. What you're really gonna say is, I can measure A and C from an ACS. I can get B from C minus A. I can get BB from this instrument. I'm just not going to have the full volume scattering function, but I'll have to live with that. And then you might say, well, I need to measure the full sky radiance distribution. One of the inputs to hydrolyte is if you have measured the whole sky radiance distribution, like from a fisheye camera, you can input that into hydrolyte. You don't have to use its little built-in models. Well, there are instruments that measure that. Ken Voss can do it, but almost nobody else can. So the best you can hope for is you maybe get an ED measurement, and then you finagle the shape of the sky radiance to go along with that. And so you can get ED, you can of course get sun angle, something about cloud conditions, wind speed. If there's a bottom, like you're working in the Bahamas, well, then you get the bottom reflectance measurements. And once again, we'll learn in a day or two about the BRDF, the bidirectional reflectance distribution function. It's basically a volume scattering function, but for surfaces, almost never measured. So the best you can do is get the irradiance reflectance of the bottom and assume the bottom was a Lambertian reflector. And you have atmospheric models that are gonna maybe compute L sky, and you can use those. Sometimes there's a model called ModTran that's the atmospheric version of Hydrolite. So I'll run a ModTran simulation to get the sky radiance distribution, and you can put clouds in it and all of that kind of stuff, much more sophisticated than the little default models in Hydrolite. But I'll generate the sky radiance distribution for exactly my atmosphere, and then I'll put that into Hydrolite. And you skip the whole step in Hydrolite where you tell it to use this RadTran model and so forth. Okay, but once again, rarely do people have that measured. So you get, you would like to have the full radiance distribution in the water if you compare it with Hydrolite. The best you'll ever do probably is LU, or maybe you get LU looking in this direction and maybe looking in that direction, in that direction, in that direction, but that's about it. So there are commercial instruments, of course, for measuring irradiances. You can do LUs, you can get maybe the above surface radiance in one direction. That's when you're doing the Carter method. And so you have something you can compare with a Hydrolite or ModTran output. Okay. Other things that you would like to know, of course, are the things you're retrieving: chlorophyll, CDOM, total suspended matter, and so forth. Those are not inputs to Hydrolite, but they're things that you're probably going to want to retrieve from your satellite. So you'd like to have in-water values of those things to validate your satellite retrieval. And when you compare a retrieved chlorophyll with what you measured, you're really validating this whole process: atmospheric correction, in-water stuff, et cetera. And you finally then get a chlorophyll. Okay, so ideally you would measure all these phytoplankton pigments. You'd have all these IOPs partitioned into phytoplankton and CDOM and detritus and inorganic and whatever. Well, in reality, you can probably get a chlorophyll profile. You can get ANC data, and maybe you get some kind of measurement of total suspended matter. That's about the best you can hope for. And then likewise for the atmospheric measurements, just like with IOP, but with Hydrolite, you need to know in-water IOPs. For ModTran or something similar, you need to know all the atmospheric information, which includes sea level pressure, temperature, humidity, wind speed, on and on and on, aerosol concentrations, and so on. And there are instruments, sun photometers, for example, that you can get at least aerosol optical depth and maybe some information about the particle size distribution of the aerosols. And then you can play with that and run your atmospheric code. But at least think about, even if you don't have a sun photometer, keep in the back of your mind that I really did need that data. If I don't have it, I'm just going to have to make educated guesses. Okay, polarization is ignored in ModTran and Hydrolite. It's coming in the future more and more. So ideally, you wouldn't just measure the radiance distribution, you would measure the full Stokes vector distribution. Well, there are a couple of people now that have instruments that can measure in-water Stokes vectors. And Ken is the only guy that's really ever measured an in-water Mueller matrix for all of the components. Although now the Sequoia, for example, has an instrument that measures the upper 3 or 4 elements of the Mueller matrix. So the 1,1 elements, the volume scattering function, and the 1,2 and the 2,2 tell you something about how the stuff that's in the water scatters polarized light. Okay, and there are atmospheric radiative transfer codes that include polarization. But once again, I once downloaded this code and it was such a mess, I never tried to run it. It's very complicated code. So anyway, enough said there. You'd like to know polarization, you're probably not going to have it, but keep in mind that 10 years from now, people may be saying you have to measure the Stokes vector. Okay, you really have to understand your instruments, what they're actually measuring, how precise are they versus how accurate are they. remember, I can have a very precise instrument that just keeps putting out the same number time and time again, and it's great. It just puts out the wrong number. So you may be better off with an imprecise instrument that puts out a spread of values, but if you take enough measurements and add them together, on average, it'll give you the right answer. So you have to think about what's important for my problem. Okay, so enough said there. Probably most people here have never heard of Haida Gwaii. If you're Canadian, you should know at least. Anyway, here I am in Seattle. So I decided I should go up and check out Haida Gwaii, see if there's any kayaking there. Well, this is Haida Gwaii. It used to be called the Queen Charlotte Islands. And starting in around 1990, over the next decade, the Canadian government said, look, we basically stole this from the Haida Indians and we ought to just give it back to them and, you know, be nice guys. So they started a process of taking the Queen Charlotte Islands and basically giving all the government or the running of the islands back to the Haida Indians who had been there for the last 10,000 years. And that's now been, you know, a completed process. The little green area down at the bottom here is a big national park and marine reserve, and it's a part of the Canadian National Park System, but it's run entirely by the Haida Indians who live here. And at the end of this process, they had a meeting between the heads of the Haida tribe and the Premier of Canada. And the Haidas are known for this just magnificent artwork. And they gave the Premier a little carved box. And he opens it up, and in the box is a piece of paper. The piece of paper said, Queen Charlotte Islands. And the Haida said, you can have your name back. We don't need it anymore. So anyway, what you do is you drive from Seattle for 2 long days, 26 hours. Then you take an 8-hour ferry ride and you get over to a place called Skidegate Landing. And then we took a water taxi for about 4 hours down to the south end. And then we kayaked back. Now, one of the reasons you go there is there are still abandoned villages that have authentic totem poles literally left over from 200 years ago. And up till about 1869, depending on whose estimate you read, there was between 10,000 and 30,000 Haida Indians living on these 2 main islands. And then in 1869, a guy from Vancouver brought smallpox, and a year later, there were 600 Haidas left. So anyway, a lot of these villages were just abandoned, and the totem poles are still sitting there. If you want to go to one of these, each village has a guy who's called the Haida Watchman. You radio him, you say, hey, you know, party of kayakers, can we come over and check out the village? And he'll say, yeah, come on over, or come this afternoon. They only allow 1 group at a time on the island, and you're only allowed to go there once because there's a demand. So anyway, we went over, we kayaked over to this island, which is called Skangwe Lanage, which means Red Cod Island. And if you look on a nautical chart, it'll call it St. Anthony's Island, if it's an older chart anyway. So you get the tour all around in this village area. There are these old longhouses. Here's the size of the beams that supported the roof of these longhouses, where you might have 100 people living in a longhouse that's basically almost as wide as this room, maybe 2/3 as wide, and, you know, as long as this building. And they're just, these beams are like this big around. It's just incredible. So anyway, that was quite a tour to get this guy's perspective on, you know, the whole history of the Haidas and the white culture, and, you know, getting it all back and all of that. And the Haida language was down to about 20 native speakers, and they were all like 97 years old. But after the Haida got control back, they've started an elementary school now, and you can enroll your kid in the 1st grade, whether you're Indian or white, doesn't matter. And they're entirely taught in Haida from the 1st grade onward. So they now have about 80 kids who are native speakers of Haida. So they pulled it off. Well, anyway, on the way back from the island, the weather forecast said, gale coming this afternoon. But we thought, well, let's see if we can, okay, somewhere there's a pointer. There it is. We started out, the waves were like 2 feet high. It was windy, 20 miles an hour, whatever. It wasn't too bad. We got about 80% of the way across this 2 or 2.5 mile crossing, and the gale arrived. And all of a sudden, in like 10 minutes, we went from 2-foot waves to 6-foot breaking waves and like the 40 maybe knot winds. We needed to go around this little point and paddling into the wind. We were literally going backwards. And we're all pretty good paddlers. So all we could do is turn around and we headed downwind, basically surfing the whole way. And you never get good photos of that, but this is from some guy's GoPro on his helmet. You can see waves breaking on the shore, these big monstrous waves. And we found a little cove that we could pull into. And, for the last 20 years, I've been carrying all of my emergency equipment, which lives in the kayak, space blanket, a little bit of food, first aid kit, all that kind of stuff. And this was the first time I actually really had to dig it all out. And so we hunkered down in the woods overnight in the driving rain and the wind and, in the space blanket. And you don't get a lot of sleep, but, that doesn't matter. And then the next day we continued on, and we had to wait out a few more days of bad weather. And then one morning we get up, it's clear weather, away we go. We paddled about 90 miles further in the next week. There was a big crossing, 6 miles. It was one of those like 2 days a year, you'll have this kind of conditions. And we did a 6 mile crossing in 1 hour and 45 minutes and ended up very nicely on a place called Hot Springs Island. And that was our last day of the trip. So I strongly recommend you go to Haida Gwaii. There's a company there that does guided kayaking tours, and you can go out with them for a week and you camp in protected waters and let them do the cooking and all of that. It's really a nice place, and you'll be blown away by the art in the museum. And it's actually called Queen Charlotte City, which is next to the ferry dock. There's the Haidas have identified about 12,000 artifacts that are in museums all around the world that were looted from their villages in the late 18 and early 1900s. And so they're now very aggressively going after all of these artifacts and try to get them some way or another, get them back. And this is everything from, the museum in Vancouver to the Smithsonian to the British Museum, you name it. They all have totem poles and such. Yeah, Ben.
If you want a really great museum of Anthropology at UBC has all of these artifacts that he's talking about. If you have a student card, it's absolutely free. And good 2-3 hour walk around.
Yeah.
And then outside of
Yeah, and it's their art. I mean, basically it rains all the time there. So what do you do in the winter? You sit around a big longhouse and you make art, and tell stories. And it's some of the best art I've ever seen in the world. Not the best native art or anything, the best art, period. Just incredible. So anyway, that's it.
and there's still living artists in groups. Hold on. And these disciples, they're Steve Carter.
Yeah, and incidentally, when I checked into the Haida language, it's a language isolate. It's unrelated to any other language in the world. Nothing to do with the languages. There's a whole group of languages spoken along the coast from Canada down to Washington State. Nothing to do with any of those. So very interesting language. I actually spent a long time talking to a Haida linguist. She was about 30 years old, had gone back to school, gotten a PhD in linguistics too. She's one of the main drivers of reviving the language. So very interesting place. Definitely go there and check it out. So it's 10 after 10 now. Start up at 10:20 again. Or you need a longer break, 10, 20? Okay, sooner we start, the sooner you're done with me.
Yes, to do a testing day, it's our last testing day. Oh, our last testing day, you guys will have access to your results that you can use for your travel. Right, you need to demonstrate that you're getting tested.